Right, so I just wanted to review one of the problems in the sample exam on diffraction. There was a similar problem in the homework, and it seems that many students are struggling with this question. So let's just take a look on how you could approach it. So you have been given a BCC iron with an atomic weight of 55.85 and the density of 7.90. We are asked to calculate the locations of the first three peaks. By location, it means 2 theta value, and then the wavelength of the X-ray is given. So first we need to do is find the lattice constant. And by lattice constant, we are referring to the A parameter. Now we know that the formula for theoretical density, which is rho, can be given by N times A over Vc times Na. In this equation, you have N, which is the number of atoms per unit cell. You have the atomic weight. You have the volume of the unit cell. And then you have the Avogadro's number. So here the volume of the unit cell is basically A cube because it's a cube, and this is how we can find the value of the A. So what it'll look like is rho equals to N times A divided by small a cubed times Na. And if you plug in the values, this will come down to 7.90 equals to 2. Now remember, number of atoms for BCC equals to 2. And putting that in with the atomic weight that is given to us as 55.85. And then you will have A cube at the bottom, and then the Avogadro's number. You can take the A cube at the top, bring the 7.90 at the bottom, and then that'll give you A cube equals to 2 into 55.85 divided by 7.90 into 6.022 into 10 to the power 23. When you solve this, you can get the value of A, again, which is the lattice constant, as 0.286 nanometers. And you can do the math and check this calculation by yourself. So once we have got the value of lattice constant, now we can proceed to find the values of the first three peaks. So let's write that. And one important thing to remember here, when asked the location of the three peaks, location refers to the 2 theta value, not the theta value. So keep a check on calculating the 2 theta value, right? I will recommend using a table or a tabular way to solve this. You could do it just by writing each step by itself. I like doing it in a table, makes it much more simpler to understand and easier to do. Alright, so one thing that you guys need to know is the allowed peaks. Allowed peaks. And this is given to you in your equation sheet. I'll write it here. Equation sheet. Right, so let's look what this looks like. For you have simple cube, you have base centered cube, and then you have FCC. And each of these lattices will have some allowed peaks. For simple cube, you will have all. So you have every plane is allowed. And again, you can use the sheet, the equation sheet that is given to you, and use that to find the allowed peaks. And then similarly, for BCC, the rule becomes H plus K plus L equals to even. For FCC, the rule becomes HKL are unmixed, which means all even or all odd. Now, if you use that system, you will get the following peaks. And again, this is given to you in the equations sheet, so you don't have to worry about remembering these values, right? So if you look at the sheet, what you will get in here is the following values. So let's write them down: 1 0 0, 1 1 0, 1 1 1, 2 0 0, and so on. For BCC, you'll have 1 1 0, then you'll have 2 0 0, and then you'll have 2 1 1. And for FCC, you'll have 1 1 1, 2 0 0, and then 2 2 0, and then so on. And you can check that these rules satisfy what is given at the top here. So once we know these peaks, what you got to do is create a table. I'll recommend practicing this table by yourself so that you can work it out in the exam as well. Alright, I will write the first column as peak number. The next column will be my plane or HKL value, right? After that, what you can write is the D spacing. And for people who have forgotten, the D spacing here refers to interplanar spacing, right? So what is the spacing between the two planes having a given notation? And what we'll use here is the formula D equals to A over root of H square plus K square plus L square. And then the next column can be sine theta. And what we'll use here is Bragg's law, which is n lambda equals to 2d sine theta. So your sine theta, or this column value, will just be lambda over 2d. Now, quick note here, you can take the n value as 1. And you have that. After that, you can calculate theta, which will just be equal to sine inverse of lambda over 2d. And then again, remember, if asked the peak location, that is equal to 2 theta, so just multiply it. Alright, so let's look at how you will end up solving it. So let's write down the planes. You have plane number 1, 2, and 3. For BCC, because it's a BCC structure, right, or BCC lattice, we know it's 1 1 0, 2 0 0, 2 1 1. And for the A value, you can note that we just calculated the A value up here, right? So A equals to 0.286 nanometers. So what that will give you is that you will get D1, D2, and D3 from here. And again, just if you're still confused, the D1 will be nothing but A divided by 1 squared plus 1 squared plus 0 squared. And similarly, D2 will be A divided by 2 squared plus 0 squared plus 0 squared. D3 will be A divided by 2 squared plus 1 squared plus 1 squared. So using this, you can get the 3 different D spacings, D1, D2, and D3. And then here the lambda the X-ray wavelength is given to you as, I guess, 0.154 nanometers. And you can just plug that in. You can plug in the D value that we just calculated, and then you can get sine theta. So you will get some value here, you'll get a value here, and you'll get a value here. Again, just if you're confused, this will be nothing but lambda over 2d1, lambda over 2 times d2, lambda over 2 times d3. All right. And then you can take the arc sine of it or sine inverse, and you'll get theta 1, theta 2, theta 3. Multiply it by 2. You should get 2 theta 1, 2 theta 2, 2 theta 3. So what this will look like at the end, if you want to understand more about what is happening, is that when you try to draw the X-ray diffraction spectra, you will have 2 theta on the x-axis. You generally have intensity on the y-axis. And your curve will, let's say, for example, look something like this. And again, this position will be 2 theta 1. This will be 2 theta 2. And this will be 2 theta 3. And this is how you can calculate the peak location. Again, try practice using this table form. It organizes all the calculations in a nice tabular way, makes it easier to understand. This allowed peaks is, I should say, given to you in the equation sheet, so you do not need to remember these. And the two formulas that will help you in this table is 1d equals to a over root of h squared plus k squared plus l squared, and then n lambda equals to 2d sine theta. Two important formulas that will help you with this question. And this is how you can solve this example problem, a problem in the example exam. The homework had a similar question which needs a little bit different approach, but you could try doing a tabular way to solve that.